Hello again everybody, and welcome back to the 7th video in the Atmel microcontroller programming series. And in this video we're going to perform pulse width modulation. So let's get right to it here. GITHUB microcontrollers and more, and take out the spaces, and then we're going to go to here and then repositories, and then we're going to go to this here, Atmel Programming Tutorial 7 Pulse Width Modulation. And we have two programs today. We're going to do first one we're going to do is using the fast PWM mode, which can only be done on certain pins, and then we're going to go over a way using timers, which will be similar to the previous tutorial, so that we can do pulse width modulation on any pin. But first let's take a look at the circuits here, and there's two of them. So here's fast PWM circuit, and let's go ahead and download this. And so we'll do save target as, and then whoops, don't want to save to there. We'll go ahead and save to the desktop, and that's good. And that's completed, and then we're going to go to PWM on any pin circuit, and then raw, and then we'll, whoops, not raw, we'll go to save target as, there we go, and save. And then we can close that, and let's take a look at those two circuits. So here's the circuit for fast PWM, and this is a pretty straightforward circuit, same power supply as the previous videos, same programming setup as the same previous video, same power and ground for the chip here on pins 7, 8, 21, rather 21 is no connect, 20 and 22, and then we have a LED on pin 11 and 12 and a matching resistor to limit current. And then here's the PWM on any pin circuit, and the only difference with this circuit is that instead of putting the two LEDs down here, we have the two LEDs up here. So you could just sort of save yourself some time and put four LEDs on your board at once, put a LED on pin 11 and 12, and then put a LED on pin 27 and 28, and then you'll be good to go. So I'm going to go ahead and pause the video, breadboard the circuit, and get the picture-in-picture going. Okay, so we have our circuit breadboarded, and we're going with a bit of a different camera setup here, so as you can see the multimeter display. The reasons for that will be apparent momentarily. So we'll go ahead and fire up Atmel Studio, and then we're going to start with fast PWM mode .c and raw, and I'll swing this over to the other screen to copy and paste out of. And then we're going to start a new project here, file, new project, and fast PWM mode, and then choose OK. And then we're going to choose 328p, of course, for our chip. And then when that comes up, we'll go ahead and rename main.c, and there we go, rename, paste in, and then Control-A, Control-C, Control-A, Control-V, paste the code in, and then we're going to do Control-M, Control-P to turn off code folding. And let's go ahead and run the project first. And I've got a bit of a different setup here, so I'm trying to work around some lamps I put in to make the lighting in this video well enough to read the multimeter screen. So it might take me a little bit more to kind of work my way around the board here. Okay, there we go. So now I'm going to go ahead and run it, and it's going to tell us to choose a programmer. And we're going to choose Atmel ICE, of course, ISP, Control F5. And there we go. So you can see the two LEDs at the bottom left of the board are both on, and because LEDs don't necessarily respond in a linear manner to being pulse width modulated as far as how bright they appear to be, and also our eyes don't necessarily perceive brightness in a linear manner. So it's kind of difficult to look at the LEDs and know that one is being pulse width modulated whereas one is solid on. So that's where we're going to break out our meter here. So I'm going to connect the ground lead to ground, of course, and then if we take a look on this pin, so we're set to voltage here. Just a moment here while I straighten out my meter leads here. So if we take a look at this pin here, we will see that we get, that's essentially 5 volts. It's 4.84 because of there's some minor voltage drop in the circuit, but that's pretty close to 5, so as we can see. So then as we go to the next pin down, so now we're going to check the pulse width modulated pin, you'll see that because we're on half the time, off the half the time, our meter is averaging out to 2.4 volts, so half of the previous reading. So then if we go back to the pin that's on solid all the time and we set our meter to read frequency, as you can see we're getting 0 hertz, there's no frequency there. But if we go to the pulse width modulated pin, we're getting 3.6 roughly kilohertz frequency. So that's working successfully for us as far as pulse width modulating with fast pulse width modulation. So let's take a quick look at the code here. Okay, so if we go to here and then we can look through here, so the top is pretty much the same as the previous programs. Here we're simply setting our two pins PD6 and PD5 to output, and then we have two registers to set, TCC R0A and then TCC R0B. So let's take a look at TCC R0A first. So we're going to set the COM0A1 and COM0A0 bits as follows, and this will give us the setting that when timer counter 0 rolls over, we're going to set pin OC0A high, and then when timer counter 0 equals OCR0A, then we're going to set OC0A back to low. And OC0A is an actual pin on the chip. And let's take a quick look at, let's see if we go back to here, first tutorial, and then ATmega 328P pinout, and then raw, and then we'll choose open. Basically, if you'd like to use the direct hardware facilities for pulse width modulation, you have to choose one of these 6 pins here: OC0A, B, OC1, A or B, OC2, A or B. So, for example, the 2 pins that we're working with today, in this particular example, are pins 11 and 12. So 11 is the pin that we have solid on, so we're just turning PD5 solid on, and then pin 12 is what we're pulse width modulating. So you'll notice in addition to pin 12 being PD6, it's also OC0A. So in this example here, we're using this OC0A output compare timer counter 0 match A output. So if you'd like to do this direct hardware oriented pulse width modulation, you have to choose one of these 6 pins. So that's going to be pin 11 OC0B, pin 12 OC0A, or down here pin 17 OC2A, and there's 3 others on the chip. I think you get the idea. So in the next example, we're going to use timers, and that you can use any pin for pulse width modulating, but we'll get to that momentarily. First, let's take a quick look at the example we're finishing up here. So we're going to set TCC R0 A, COM0, 1A, and 0 A0 bits as follows to use these settings, and we're not using COM0 B. So we'll just leave those at 0, and then we have our wave generation mode bits. We'll find if we look in the datasheet, if we set the WGM bits to 0, 1, and 1, that will give us fast PWM mode. And these are not used in fast PWM mode here, OC0A or B. And then of course bits 4 and 5 we can simply leave at 0, and we're going to get the fastest possible pulse width modulation, we're not going to use any prescaling. So then at that point it's simply a matter of here is where we're turning PD5 on all the time, and I'll bring up the dependencies to get rid of that red underline, and it'll disappear in just a moment here. And so here's where we're turning PD5 on solid, and then here's where we're setting OCR0A. So if we set this as follows, then that's going to pulse width modulate the LED ideally at half brightness, but again, because our eyes don't have a linear response to brightness necessarily, it appears more than half bright. But the idea is that indeed it's on half the time. So, and then here we have our while loop, and notice that we don't need an interrupt here because of the way that we've used this fast PWM mode with the wave generation mode bits. It's sort of handling that directly in the hardware for us, so we don't need to write an additional software interrupt routine if we're using the direct hardware method. Now in this next program, so let's go ahead and get the next program going so we can close out of here, and then we'll open up Atmel Studio again. And then we're going to go back to here, and in this next program, which is very similar to the timer compare match example from the previous tutorial, so we're going to do PWM on any pin. That's essentially just what we're doing, only with a shorter time frame to achieve pulse width modulation. So we'll move this over to the other screen, and then let's see, we'll copy and paste the name out of here, and then file, new project, go ahead and paste the name in, and then GCC executable project, and we're using the 328p, and then we'll do that, and just another moment here, and then we'll rename main.c, and there we go, main.c, whoops, okay, there we go, rename, paste that in there, and then we'll paste in the code, and then Control-M, Control-P to turn off code folding. And first we'll run the program as a proof of concept, and then we will take a look at the code momentarily. So it's going to ask us to pick a programmer, of course. So Atmel ICE and ISP, and then we'll run it again. And so now we're using the two LEDs at the top right of the board. And again, you probably can't really see that well on camera. I can tell you, looking at it in person, I can see the LED at the top is a little bit dimmer than the LED that's one down, but it doesn't really appear half as bright necessarily. And of course that depends on the lighting as well, and everybody's eyes are going to respond a little bit differently. So let's go ahead and probe it. So we're set to voltage, so we should get about 4.9 here. So there we go, minus some minor voltage drops in the circuit. That's essentially 5 volts. And then we can go up to here and we'll find that we get half that amount. And then if we go back to the pin that's solid on and we go to Hertz, we should, okay, whoops, just slipped out there. Okay, we'll find that we get 0 Hertz, just as we would expect. And then if we go to the pin that's being pulse width modulated, you'll see that we successfully are pulse width modulating that to about 3.8 kilohertz. So that's working well for us. Go ahead and turn this off here and jump back over to the computer. And we'll take a quick look at the code. Again, this is very similar to the compare on match timer example from the previous tutorial. So this part here is essentially the same. Here's where we're just setting our two outputs, and I'll go ahead and pull up the dependency to turn off those red underlines. And there we go, those should disappear in just a moment. So now we have 3 registers to set: TCC R0A, TCC R0B, and TIMSK 0, and then we set our compare value. But first let's take a look at the registers. So TCC R0A, we don't need these COM bits, and we're going to set the wave generation mode to be 0, 1, 0, and that's going to give us the CTC, that is clear timer on compare match mode. So in other words, TCNT is going to count up until it gets to the value in OCR0A, and then at that time the timer interrupt will run. So here's the value that we're setting in OCR0A, and we're purposefully picking the lowest possible value that we can so that the ISR runs as often as possible to achieve nice smooth pulse width modulation. And here's how we're going to title our interrupt: timer 0 comp A vect, because of course it's compare A. So then going back up here for just a moment, let's see, we already covered TCC R0B. Actually we didn't, but let's take a quick look at that now. So we don't need the force output compare A bits, and there's the other WGM bit, and then we're using a clock prescaler here of 64, and we could achieve faster pulse width modulation if we use less than this, but depending on what OCR0A is set to, if we used a value that's less than 64, the interrupt might not have enough clock cycles to complete before the next time it's signaled, and that could cause some confusion and might not allow the PWM signal to flow up and down well. So I'd recommend that you use at least a value of 64 here, and then you can set this OCR0A as low as you like. So let's take a look at the last register here, TIMSK0, and of course this is pretty straightforward. We're setting the timer 0 output compare match interrupt enable, interrupt A enable I should say, and we don't need to set the B interrupt enable or the overflow interrupt because we're not using those. So then, as we saw earlier, we jump down here. Here's where we're setting PC4 on solid, and then we set the compare amount for the pin that we're pulse width modulating, enable interrupts of course. And then in our endless while loop, every so often when the timer overflows, this will execute, and then we toggle PC5. So that completes this tutorial. Hopefully that was a helpful introduction for anybody wondering about how to perform pulse width modulation on the ATmega 328P, and I'll see everybody in the next one.